to page 355, problems 47 to 63 odd. Okay. So you guys have dealt a little bit with exponential equations. Yeah, we're getting, this chapter is exponents and logarithms. So I'm going to need to remind you of a couple things and maybe teach you a couple new things. So 355, we're looking at these story problems. Okay, so there are sort of three different exponential equations, and they're really all the same thing, but the one equation will take care of everything except we sort of have a different equation on either end. So the equation that we studied when we did logarithms was y equals b times m to the x. This is the most simple exponential equation. So let's say you had $120 and you were gaining 5% interest for 6 years. Then we just plug these numbers in. So we would say y equals 120. How do you increase 5%? 1.05, good. And then for 6 years, and you could plug that in and figure out how much there was. Now, if I give you any three of those, you can solve for the fourth, but if x is not given, then you require logarithms. Okay, so that's kind of where we're headed. Now, this is called simple interest. Okay, it is compounded. I mean, it's compounded once a year. The interest is paid at the end of the year. So your money has to be in there for an entire year, and then at the end of the year, they say, okay, you've had $120 in there. We'll give you 5% of that 120. So we get paid 5% interest one time per year. Well, what if instead of getting paid at the end of the year, they paid you every 6 months? So you got 6 months worth of interest, and then you got another 6-month set of interest later. So let's look at some of these numbers. So 120 times 1.05 raised to the 6th. Well, let's just raise it to the 1st. That might be a little easier to see. So if we raise it to the 1st, at the end of the year, we have $126. Okay? If we did the same calculation, 120 times 1.05, and we raised it to the half year, so in July, they pay you 6 months worth of interest. You're going to make $2.96. Okay? But now, instead of having $120, we now have $122.96. So if I times that by 1.05, raised to another 1/2, which represents the second half of the year, we're going to end up with a little bit. Wait, that didn't work. Huh. Answer times 1.05. That didn't work. What did I do wrong? Huh. We'll get there. Although I'm really confused why that didn't work. Huh. Well, the good news is we were never going to do it this way anyway. So, but that extra $2.96 is going to earn you more interest and it's going to end up, you'll have a little bit more. But apparently nobody does it this way because it doesn't work, which really confuses me. So if you look in your book, look back at page 351. 351 gives you the equation. And our original equation, y equals b times m to the x, only works if you get paid interest one time at the end of the year. This compound interest equation, principal times 1 plus the rate over n raised to the nt, we've added this variable n. N is the number of compounds. So if n is 1, you plug in 1, and this equation is going to simplify to be that. So when n equals 1, you can see we get 1 plus the rate, which is where our 1.05 came from, and then 1 times t is just time. So if n equals 1, then this equation and that equation are identical. Okay, so if I plug in the information that I just used, 120, and I'm going to multiply that by 1 plus the rate, which is 0.05, divided by 2, that's the number of compounds, and I'm going to raise that, and if you have the older calculator that actually puts the caret, you need to put parentheses around this. If you have the new software like I do, you can just do 2 times the 1 year. And you'll notice we earned an extra 7 cents. Well, banks are happy to round. They'll round your money down, and they'll round what you owe them up. So, and you might think those little half cents aren't going to make a difference, but over the course of millions of transactions over a year, it helps them out. So, yeah, if they're paying you, they're probably going to round down. So what happens if instead of paying out every 6 months, I pay out every 4 months? So now I'm going to change this to compounding 3 times a year, which would be every 4 months. Oh, I messed up. I put a 4. So this is, n is not months, it's the number of compounds per year. So 4 months would be 3 compounds a year. So now I've made 10 cents more than my original. So let's do this calculation. So 120 times 1 plus 0.05 divided by, let's do 1, raised to the, raised to the 1. Let's go out to the original 6 years. So compounding once at $120 is going to gain $40.81. Okay. So now I'm going to compound twice. So change that to a 2. Change this to a 2. And the difference is, what, 50 cents? 57 cents? Not a lot. Now, if your interest rate goes up, or if if years is a lot longer, then it's going to make quite a difference. Now, let's compound it 9 times a year. So my original number is 160.81. So I'm going to change this to 9. And I'm going to change that to 9. So that's a whole $1 more. We're doing well. Well, banks actually compound every day. Except if they're charging you interest, they'll compound it 365 times. If they're paying you interest, they take certain days off like Christmas and Thanksgiving. So it's usually 360. So I'm going to go in and I'm going to change it to 360. So 360. And then 360 times 6. So if we compound every single day, so at the end of the day, the bank looks at your account and they calculate the interest. Now, most banks don't pay the interest on that day. Mine pays me every 3 months. So they hang on to that interest, they hide it away and don't tell you what it is. And it's not in your account, so it doesn't earn interest on itself. So it's calculated every day, and then at the end of the 3-month period, they deposit it in your account. So it depends on when the interest is paid out. But if they actually paid you every day, then that's a whole $1.26 more. Now, what if we compounded every hour? So what if we compounded every minute? And what if we compounded every second? So I'm going to go in here. So I'm going to go into this 360, and I'm going to put in a really big number. So 1 million. What if the bank pays me $1 million, they pay me 1 million times in the year? Well, actually, why don't we do every second? There's 31 million seconds. So 31 million would be every second. Oops. So parenthesis 31 times 6. It's really not going to go up that much. No, it's 0.3 cents. So the difference between daily and every second is very, very small. So if you go from one compound to 2, you're actually going to gain quite a bit. If you're going to go from 2 to 3, you're not going to gain as much as you did on the first one. And from 3 to 4, every time you go a little bit higher, the gain is smaller and smaller and smaller. And this equation actually has a limit. So if I typed in 31 billion, I'm probably not going to see much of a change at all, maybe like 1,000th of a cent. It's going to be very, very small. So what happens if we compound an infinite number of times? And you might say if you're compounding infinitely, your answer is going to be infinity, but it's not. The more times you compound, the slower the growth becomes. So we actually have an equation if we plug in infinity. So if you look at this, p times 1 plus r over n to the nt. If we plug infinity in there, what is r divided by infinity? What's any number cut into an infinite number of pieces? How big would each piece be? 0. So this actually goes away, and I get p times 1. What is infinity times time? Infinity. And what's 1 to the infinity? Well, it's not quite that easy. Once you start dividing by infinities and raising to infinities and 1 times itself an infinite number of times, it's a little bit messy. And what we found out is this equation with infinity plugged in here and in here approaches p times e to the rt, where e is an irrational number. It's 2.71, goes on forever. And there's no way to actually plug in infinity. Because technically you can't divide by infinity, and you can't raise to infinity when you're dealing with ones. So the graph approaches p e to the rt, and once calculus was invented, we figured out a way to actually do it. And that equation perfectly models infinitely compounded. And certain things actually do that. Growth of living things follows the PE to the RT. Population growth, anything that's always happening all the time, it doesn't use the compound interest model. It uses PE to the RT. So there are three equations you need to know. Y equals B times M to the X. That's compounded once a year. P times 1 plus R over N to the NT. That's really only used in banking, where the compounds are defined specifically. Once a week, once a month, once a year. And then anything that happens in nature, which is always increasing, we use PE to the RT. Okay? Now, because that E is so prevalent, we need a log base E, and that's why the natural log is so important. That's why there's an LN button on your calculator. There's a log base 10 button because we have 10 fingers, and our numbering system has 10 numbers. But we don't actually use the log base 10 button very often. The LN button is way more useful for exponential equations. Okay, so I'm going to do 48, so you guys can do 47. In 2004, the population in Morgantown, Georgia was 43,000. The population in Morgantown doubled by 2010. If the growth rate remains the same, what is the expected population in 2020? Is this compounded once, compounded multiple times, or continuous? It's continuous. It's always changing. So we're going to use PERT. So that is my principal. That's P. So 43,000 times E, and R is unknown, right? And what's T? We're looking at how many years? 6 years. So 6R. Okay? And what is this going to equal after those 6 years? $86,000. How'd you get that? It's double. So 86,000. Now the really cool thing about this is I divide by 4,300 or 43,000. What am I going to get? 2. So if you know it's going to double, the actual population doesn't matter. We could have said 1 e to the 6r equals 2. Because the doubling time is tied to the rate, not to the original amount. So if this was 4, that would be 8. If this was 6, that would be 12. So if you're doubling or tripling or anything like that, they don't even need to tell you how much there was originally. You can always just set it up as you have $1 and you turn it into 2. So we get e to the 6r equals 2. Do you remember how to solve that using logarithms? Take the ln of both sides. So ln of both sides, and you drop the 6r. So 6r ln of e equals the ln of 2. Well, what is the ln of e? It's just 1. So that cancels, and then we divide by 6. So the ln of 2 divided by 6, so 0.1%. Okay? All right, 47. So there were 7.1 million people living in London. If the population is expected to double, oh, we're not done. Sorry. So we have 0.11. So if I take this original 43,000, and then e to the 0.11, times how many years is it from 2004 to 2020? 16. So I need to 43,000. And then if you do second ln, you get e raised to the 0.115 times 16. So that population would be 270,000. Okay? So 11% is a lot, right? So it's growing pretty quickly. Okay. If the population is expected to double by 2090, what is the expected population in London in 2050? So to start off, do I even care how many people there are? No, if it's time to double or time to triple, you might as well just say one person, e raised to the r times, how far is it from here to here? 82 years, 88 years, and I want it to double. You could put in 7.1 million and 14.2 million, but when you divide by 7.1, you're going to get 2. Okay? So how do we solve for that? ln both sides. ln, drop the 88r. 88r ln of e equals the ln of 2. But the ln of e is 1, so we're just going to divide this by 88. So ln of 2 divided by 88. So that would be 0.7%. Now what do we do? So 0.01 would be 1%. So 0.007 would be 0.7%. So now I need to take the original 7.1 million times it by e to the 0.0078 times how far is it from 2002 to 2050? 48 years. So 7.1 e. And whenever you're dealing with exponential equations, the more numbers you put in the rate, the more accurate you're going to be. And small differences will make a large difference in your answer. So I recommend doing second answer. And then you get all of those numbers. And then we'll times that by 48. So 10.3 million. Okay. Let me look through some of these others. Okay, let's do 49. Suppose an investor buys land in a rural area for $1,500 an acre and sells some of it 5 years later at $3,000 an acre and the rest of it 10 years later at $6,000. Write a function that models the value of land in the area, assuming the growth rate stays the same. What would the expected cost per acre be 30 years after the initial investment? This is an involved problem. So we need to pick a variable. So per acre, 15,000 or 1,500 per acre. So his initial cost is this much. He sells some of it after 5 years for 3,000, and the rest of it 10 years later at 6,000. I'm not even sure this is worth our time. Well, let's try this one and see how it turns out. I haven't done it yet. So models the value. Nope, never mind. Never mind. Sorry, guys. Okay, 51's a lot better. Radioactive isotope of selenium, which is used in medical imaging of the pancreas, has a half-life of 119 days. If 200 milligrams are given to a patient, how many milligrams are left after 30 days? So we know the half-life. We don't know the decreasing rate, right? The selenium, is it compounded or is it continuous? It's going to be continuous. So if I had some amount, some unknown amount, so P, E raised to the R is unknown, and it takes 119.77 days, what am I going to set that equal to? What do I put in for P? I could put 200, or 2, or 8, or 1/2, or 65, or anything I wanted. What do I know about this number compared to that number? It's twice as big. So I would do what CJ wanted to do, stick a 2 here, and if that's 2, what's going to be here? 1. And now I have to divide by 2. So really, you could just set it up like that. If we have 1 on one side, we would have 1/2 on the other. And then we do the same trick, ln both sides, this. So 119.77 R, and then the ln of E cancels, equals the ln of 0.5. I'm going to divide by 119.77. So ln of 0.5 divided by 119.77. Does that make any sense? Why? It's decreasing. It's going down. How fast is it going down? 0.5%. So we're decreasing by 0.5%. Now that we know the rate, we can go back to our original problem and do this. So if we start with 200, e to the negative 0.005 times 30, that will give me the future amount. Does that make sense? So 200 times e, nope, wrong button. 200 e, and second answer is always a good idea here, times 30, 168. Is that not what did you get, Maddie? Yeah, if very small differences in your rate will make rather large differences in your answer. So second answer is always a good idea when you're dealing with logs or exponents. Big logs. Okay, so 53, I want you to do that one. 55. You can do 55. 57 is really easy. 59 is easy. Yeah, I'll answer that in just a second. 61 is easy, and 63 is not too bad either. So if you're talking about half-life, doubling, tripling your investment, you're always going to have e to the RT, and I would always put 1 there, and then the number on the other side, that is your double or your half or your triple, and that's the easiest way to do it. So you could fill in any values you wanted, and then, so if I put 4 there and I'm doubling, then I would put 8 there, but when I divide by 4, I'm going to end up with a 2 over here. So I might as well just start with the 2 on the left side. If you're doing radioactive decay, it will always be half-life. And when you're dealing with half-life, you're going to equal it to 1/2. And if it's radioactive decay or any other type of decay, your R value is going to be negative. Okay. So do all of the problem set except, what was it, 49? Don't do 49. Okay. Good luck.